Okay, let's go ahead and begin the physical and chemical controls of microbes. This is chapter 11. This unit is going to cover chapters 11, 12, 13, and 14. Um, this is kind of and 15, but it's a little bit out of each chapter. It's not a huge, great big bunch of the whole chapter. So bear with me. We're going to do this in small pieces. So you will have a number of different, it'll go chapter by chapter. Your study guides will go chapter by chapter. So hang with me and we'll get through this. This is actually a pretty small unit. It's not going to overwhelm you. So um, let's get moving. When we are looking at microbial control, one of the things that we need to understand is that if we don't control microorganisms, they will take over. They are ubiquitous in the environment and do require some sort of microbial control. When we control them, we can go from an extreme of sterilization where we are destroying every type of microbial life. This is essentially the destruction of all living organisms. Or we can go to something like disinfection and antisepsis, which destroys microbial life on inanimate surfaces or on living surfaces. If we're talking about disinfection, this is going to be reducing contamination on some sort of inanimate surface, whereas antisepsis is going to reduce contamination on some sort of living tissue. We can also have decontamination, which is essentially a mechanical removal of the microbe, and this can be on animate versus inanimate surfaces. When you wash your hands, this is a decontamination process. Pardon me. There are three methods of microbial control: physical, chemical, or mechanical. I love this flow chart because it really divides things very accurately. You'll see that none of these will overlap each other. You have your physical agents. This is going to be something that is going to deal with the environment that the microbe is living in. We can divide this into heat and radiation. Our heat, we can have dry heat or moist heat. With each of these, we can see that we can divide things down, and we can see if they disinfect or if they sterilize. You'll notice that physical agents are going to be disinfection rather than antisepsis. If we go over here to chemical agents, we can divide those into gases and liquids. Those disinfectants are going to be things that, again, will reduce microbial life to a safe level, whereas sterilization is going to destroy everything. In antisepsis, again, this is going to be kind of like disinfection, but on living tissue. And if we go over to mechanical methods of control, this is going to be like filtration. This is going to be filtering air and liquids, and this is the process of decontamination. Microorganisms, like I said earlier, are ubiquitous, and they can cause infection or spoilage just for the simple fact that they are constantly present in the environment. If we are to put milk into a refrigerator, we can control that microbial growth to an extent. But if we take that milk out and put it on a counter, that bacteria that's in the milk is going to go ahead and spoil the milk, even if we don't ever open the container, because they are present in the milk itself. Contaminants that need to be controlled go from soup to nuts, everything from bacterial cells and endospores to things as deadly as prions. You can see the list here of everything that needs to be controlled. This is a table that basically tells you the relative resistance of bacterial endospores versus vegetative cells when we talk about control agents. If you look here at this first one, we're looking at heat. We're in this case using something called moist heat. You're going to need, in order to control endospores, you're going to need to bring that heat up to 120 degrees centigrade. Vegetative cells will be consumed at 80 degrees centigrade. If you follow this chart down, you'll see that it takes a significantly higher dosage of the the control method to kill the endospores or to control the endospores as it does to the vegetative cell. Let's talk first about sterilization. This is going to remove all viable microorganisms, including viruses. Sterilization destroys all organisms. The materials, once they have gone through a sterilization process, are considered sterile, and these materials generally are going to be inanimate objects. When we look at sterilization and some of the processes of sterilization, we're going to see that they can be pretty significant and could be deadly to living tissues. Probably the most common source of sterilization is going to be using heat of some sort. There are chemicals that are called sterilants that can be used. Ethidium gas. This is going to be a gas that we use to do things that are heat labile, things that are going to be destroyed by heat. Petri dishes are going to be sterilized using some sort of a gas, and this gas would be a sterilant. With disinfection, this is not going to be as significant as sterilization, because this is going to be a physical or chemical process that is going to destroy vegetative cells only. It is not going to destroy endospores. Disinfection is usually on inanimate objects. It also has the ability to remove toxins. Most organisms that produce a toxin, that toxin is a protein. And if we use some sort of a chemical agent or some physical process of disinfection, it's going to break that protein. And when that protein is broken, then it doesn't work anymore. A good example of this is going to be like a 5% bleach solution. Very effective at killing a good number of vegetative cells. Antisepsis is just like disinfection, except for living tissue. Basically, the chemicals that we use are called antiseptics. These are going to be applied directly to body surfaces to destroy any sort, again, of any vegetative pathogen. They are, again, not going to be effective against endospores. What we are trying to do with antiseptics is we are going to try and prevent the entry of some sort of infectious agent, and this is the process of asepsis. What we are doing with asepsis is trying to prevent sepsis, which is the growth of microorganisms in the blood or other tissues. When we look at the agents that we use, these are going to be divided into agents that kill versus agents that inhibit. If you have an agent that ends in the suffix CIDE or side, like homicide, suicide, those are going to be to kill. Those are going to be things that, if you have something that is a bactericide, these are going to destroy bacteria. Something that is a sporicide, this is going to destroy bacterial endospores. Virucide, and the list goes on. If something is static, STATIC, or has the suffix stasis, these are going to be things that inhibit. They are going to keep the bacteria from being able to go through cell division, but they are not going to kill them. They are going to basically keep them at a level where they are safe and don't cause harm. When we use decontamination, this is going to be a process that's going to be used when sterilization is not required, but we need to decrease the number of infectious agents to a safe level. This is going to be used a lot in the food industry. Sanitation is a process that those kinds of industries use that are going to be a cleansing process that is going to mechanically remove microorganisms to a safe level so that when you consume the food or consume the drink, you are not going to be infected and get sick. Sanitizers, these are going to be compounds like soaps or detergents that are going to be used on surfaces. They're going to be used on body tissues to eliminate harmful bacteria. If we're talking about the sanitary conditions of the food processing area, they can be, they will not be free of microbes, but they are safe to use at a normal level. Let's talk about your kitchen. If you are somebody who has a relatively clean kitchen, as clean as anybody else's kitchen, your kitchen is probably sanitary. It is safe to go in and cook in, and you wipe down your counters, you do all those kinds of things to keep things sanitary. Degermination is a process that we use in decontamination that is going to reduce the numbers of microbes on the skin using hand sanitizers, washing your hands. These are all processes that are going to allow you to degerminate or degerm the body system. We do have some practical concerns in microbial control. First of all, does the application require sterilization, or is disinfection adequate? Washing my dishes, I don't need to sterilize my dishes, but I do need to wash them. So sterilization is not required, but disinfection would be. Is the item to be used, to be reused, or is it permanently discarded? And if we do use it, can it withstand heat, pressure, radiation, chemicals? These are all things that have to be considered. If it's something that is going to be reused, there are certain chemicals that maybe you certainly don't want to put on them, because if you're going to, like, say, an instrument that's going to come in contact with living tissue, those kinds of things. So those are considerations that need to be taken. Is the control method suitable for given application? Washing my silverware is certainly suitable for the purpose of that silverware. Okay, putting a scalpel in a dishwasher is certainly not suitable for the method. That scalpel needs to be sterilized. Will the agent that I'm going to use be able to penetrate to the necessary extent? Is the soap or the detergent or whatever that I'm using going to be effective? And is the method that I'm using cost and labor efficient, and is it safe? One of the things that you must look at is the chemical or the process that I'm using safe for the person applying the process. So again, these are some considerations that need to be made. When we look at bacteria, we want to know what constitutes microbial death, and there are three characteristics. And if you have microbes that fall in any one of these, they are well on their way to microbial death. If you have a microbe that has structures that become dysfunctional, which causes the entire cell to sustain irreversible damage, this cell is on its way to dying. If the cell can no longer reproduce under ideal environmental conditions, you don't have to give it something special to keep it growing. This cell is on its way to microbial death. And death is going to begin when certain concentrations of some sort of microbial agent are met, and this is going to cause cells then to begin to go down into this logarithmic manner, where the cell population is decreased by half with every interval. This picture is a picture in your book, and if we look here, you'll see that there are 4 different categories of microbial death, the way that we can look at it. The first one is the length of exposure. If I have bacteria exposed to a particular chemical for a certain period of time, the length of exposure, the longer it's exposed, theoretically, I should be able to reach 0. If I have an endospore forming organism, however, I'm always going to have the potential for sporulation and growth. Microbial load, obviously, the more bacteria I have, the longer the time it's going to take to reach sterilization or to reach some time of or level of decontamination. The lower number of bacteria I have, obviously, the less amount of time. Spores versus vegetative cells. Those spores are going to live on and on and on, and eventually these vegetative cells I should be able to reach 0 on. And then the action of an agent. Do I have something that is a static control, which by definition the cells would be capable of growth until that agent is removed? Or am I using some cytal control agent that is going to cause that logarithmic decline in my bacterial population? You do have some factors that influence the action of these microbial agents. The number of microorganisms. How many microorganisms do I have? Am I overwhelming my agent? What is the nature of the microbial population? Do I have spore formers, or are they all non-spore formers? What happens if I increase or decrease the temperature? What happens if I increase or decrease the pH? These are all going to have an effect on the action of the agent. The concentration of the agent. Do I have to use it 100%, or can I dilute it down? What is the mode of action? What is the target? How does it work? So if I have a cell that is resistant, then obviously this agent is not going to work. The presence of some sort of interfering matter. A lot of times you'll have organic matter that these bacteria can use as a nutrient source. If they have that, then you're going to have a much harder time getting rid of those organisms as opposed to those who are in places where there is no organic matter or solvent or some inhibitor. The modes of action of these antimicrobial agents are going to be, how do they work? What is their mode? What is their mechanism of action? There are 4 targets of these antimicrobial agents. First one is the cell wall. The second one is the cell membrane. Then you have protein synthesis and nucleic acid synthesis. When we talk about the modes of action of agents that target the cell wall, their mode of action can be to block the synthesis of the cell wall completely. If the bacterial cell has no cell wall, then that cell is going to die. You have agents that will digest the cell wall. Their mode of action is peptidoglycan digestion, or the protein digestion in the cell wall. They can break down surface proteins as well, and then they can also cause these cell walls to become fragile, and they will lyse very easily. The cell will split open and will eventually die. Surfactants are a good target for the cell membrane. Surfactants are anything that will incorporate itself into the membrane, and it will create holes in that membrane. So extracellular fluid flows in, intracellular fluid flows out. Soaps are a good example of a surfactant. Surfactants have often been said to call water wetter. Okay? Here we have a picture of a surfactant. Basically, these surfactant molecules will insert themselves into the membrane, and when they do, it causes this membrane to kind of fall apart, and now we have these large holes where the intracellular fluids can flow out, the extracellular fluids go in, and the cell will eventually rip apart. Protein and nucleic acid synthesis inhibitors, a lot of times they deal with in protein synthesis, they are going to interrupt translation by binding to ribosomes. They're going to bind to those ribosomes, keep them from functioning, and we don't end up with our protein. You can have them binding irreversibly to DNA, pardon me, and they prevent the transcription translation process. They prevent the production of the nucleic acid RNA. They prevent the completion of protein synthesis and translation. Some of these agents can also be mutagenic agents, meaning that they're going to cause mutation in the DNA, which interrupts DNA synthesis, and these things will shut down, and the cell can't go through cell division. If we look at this picture, one of the ways that some of these physical agents can work is to take a protein. We have our normal native protein, and if we apply something like heat or we change the pH, we can have what they call the complete denaturation, where you go straight back to that primary structure of the protein. Or you can have it go from its natural shape to a different shape of that protein. And once you have that different shape of that protein, now you have a totally different function. And generally that function is non-function, because the active sites are closed off now and there's nothing to allow this enzyme to function. If we come over here and we add something like a heavy metal, we can block the active site. So we can have enzyme repression or competitive inhibition of this particular protein. So these physical controls then can stop the process of protein function. Here are some methods of control. We're going to talk about heat, we're going to talk about cold, we're going to talk about radiation, all different kinds of methods of control. Probably the first one, and the one that is most widely used, is heat as an agent of microbial control. Think about it. When you take a shower with hot water. When you wash your counters down after you've prepared food, you use hot water. So this heat is a way to control microbial growth. When we elevate temperatures, the microbe will generally die, because the cell itself can't adjust its internal temperature, and so you have proteins then that become non-functional and the cell dies. So elevating the temperature can actually be bactericidal. If you lower temperatures, this is a static control, because think about your milk. If you take your milk and put it in the refrigerator, it stays for quite a while. But if you put that milk out on the counter for a day, that's going to clabber and it's going to become um, unpotable, and it will be spoiled. You can use either moist heat or dry heat. You're going to see that there is a difference between moist heat and dry heat. If we look at the control mechanism, the comparison, at 121 degrees centigrade for moist heat, we can sterilize in about 15 minutes. If we're talking about dry heat, we're at 121 degrees centigrade. This is about 600 minutes or 10 hours. So it's going to take quite a while for this to get hot, or excuse me, not get hot, but to sterilize. And if you look here, it doesn't take, once we get up to 134 degrees centigrade, we can reach sterilization in about 3 minutes. We never get anywhere close to that, even at 170 degrees centigrade, which is somewhere around 325 degrees. So you're going to need a lot of dry heat to reach sterilization in a quick amount of time. There are some thermal death measurements that will help us to understand how effective heat is. Temperature and length of exposure have to be considered when we're talking about disinfection or sterilization. Higher temperatures generally are going to constitute lower times of exposure. The hotter it is, the less time it takes. But there are some times where lower temperatures are going to be required, so this is going to require a longer exposure time. There are two measurements, thermal death time and thermal death point. Thermal death time is the time that it takes to kill a population of bacteria at a specified temperature, whereas thermal death point is the lowest temperature required to kill a population of bacteria in 10 minutes. So each of these are going to be different for every organism that you look at. E. coli has its own thermal death time, its own thermal death point. Staph aureus has its own thermal death time, its own thermal death point. So this is going to be different for each microbe. Here is a table that basically gives you thermal death times of vegetative organisms. Again, endospores, you're going to have to use more than just heat to destroy them. When we're going to talk about destroying endospores, we're going to use something like with steam under pressure or heat under pressure. Basically, when we put water into a pressurized system and heat it, it is going to raise the temperature of the steam. It goes from 100 degrees centigrade to 121 degrees centigrade. An autoclave is a perfect example of how this is used. I will show you the autoclave that we have if you want to see it, and show you how it works. Basically, it is the most efficient pressure temperature combination in an autoclave at 121 degrees centigrade at 15 pounds of pressure per square inch. Basically, at this combination, you can reach sterilization in 15 to 30 minutes. You can sterilize with non-pressurized steam, and this is called intermittent sterilization or tendilization. Essentially, you have a free flow of steam over the materials that you want to sterilize, and this free flow of steam is going to occur for 30 to 60 minutes. You're going to incubate this for 24 hours, and then you're going to treat again, and you're going to repeat this for 3 days in a row. If you skip a day, you have to start all over again. So this is not something that is going to be very effective unless you have products that will withstand the heat, but they won't withstand the pressure. Pasteurization basically is used to disinfect beverages or dairy products. Heat is going to be applied in a liquid form to your product in a liquid form, and it's going to kill any potential agent that could cause this to spoil. This is going to help to retain the liquid's flavor, the food value, whatever it is, whether it's a dairy product or whether it's a distilled liquor or whatever pasteurization process gets used. We pasteurize lots of juices. Apple juices, for instance, are pasteurized. You have some specific methods. The first one is called the batch method, where you're going to expose your fluid, your product, to temperatures that range between 63 and 66 degrees centigrade, and you're going to hold them there for 30 minutes. Then you're going to have the flash method. This is basically going to be where you expose your material to 71.6 degrees centigrade for 15 seconds. Then the ultra method, or the ultra high method, is exposure to 82 degrees centigrade for 3 seconds. Once you've reached these temperatures, whichever method you're going to use, you hold it there for the appropriate amount of time, and then you rapidly cool this. This is going to produce plasmolysis, or lysis of the plasma membrane to the cell. And once that membrane ruptures, then everything in the extracellular can go in, anything inside can go out, and the cell is going to die. This does not kill endospores, nor does it kill something called thermoduric microorganisms. These are organisms that can withstand relatively high temperatures for short periods of time. Boiling water is a good disinfectant, but it does not sterilize. It will not kill any endospores. Essentially what you do is you bring your water to boil, you immerse your material, your whatever it is you're going to try and disinfect, for 30 minutes, and then once it's brought out, it can cool down and it can be used and will be safe and disinfected. We can also use dry heat as a method of sterilization, as well as a method of disinfection. If we talk about hot air versus incineration, incineration essentially ignites and reduces microbes to ashes and gas. This you would think would be sterilizer, but it does not sterilize. It essentially, spore-forming organisms can survive incineration, but it does kill most of them. This incineration is a common practice. You guys use this in lab. Every time you put your loop into your Bunsen burner, you are incinerating bacteria. There are also tabletop incinerators, infrared incinerators. That's what this little number is here. I have one of these in the prep room where I use that instead of a Bunsen burner. Basically the same process. You're just essentially incinerating your loop and killing anything that's sitting on top of it. You can use a dry oven, just like the oven that you have in your house, to achieve sterilization. Basically, you're superheating the air. You're going to bring that air to 150 to 180 degrees centigrade, which is roughly 300 to 350 degrees Fahrenheit, and you're going to hold it there for 2 to 4 hours. Essentially, this is going to be a good source for heat-resistant items, but can be destroyed by water. Things like powders a lot of times can be dry heat sterilized. So if you needed to sterilize something at your house, you could take your oven to 350 degrees and put whatever you're trying to sterilize in there for 4 hours, and when it comes out, it would be sterile. Lack of heat can also be a process to control microbes. We can slow the growth of cultures of microbes by storing them in a cold environment. When we put things into a refrigerator or a freezer, we are slowing down the growth process, but we are not killing them. So like if I need to keep a culture for a certain amount of time, I can grow it up on a media surface and then put it in the refrigerator, and it will last. Matter of fact, my media will dehydrate before my microbe is dead. So it will just kind of slow things down to the point where metabolism is almost undetectable. Freezing is a way to actually preserve cultures. I'm going to kill a lot of them, but remember, I only need one to start a new population. Desiccation is also a process that can be used for microbial growth. This is essentially dehydration of vegetative cells. You're going to make a suspension, and you're going to expose it to normal room air. Let the liquid evaporate, and you're left then with these cells that have essentially had all of their water removed, and most of them are going to die. Lyophilization, this is essentially a combination of freezing and drying. You're going to go in and you're going to freeze this to minus 80 degrees centigrade, and then you're going to take the fluid out by a vacuum. This is going to leave you a little pellet that will be viable for theoretically ever. When I first started working here in 1999, I was in the lab and I found some cultures from 1968 that were lyophilized cultures, and I reanimated them. I brought them back up through cell suspension, and they were actually just fine. So those cells survived for over 30 years in that animated state, or excuse me, in that lyophilized state. We can also use radiation as a microbial control agent. We can either use what is called ionizing radiation or non-ionizing radiation. Essentially what happens is we are going to cause the release of energy from atoms within these rays, these radiation molecules, and they are going to be flung out at such a high velocity that they can go straight through matter. And when they go through this matter, then they are going to break it. For instance, they can go straight through a DNA molecule, break that molecule, and now the cell is going to die. There are 3 types of radiation: gamma rays, X-rays, and ultraviolet radiation. Ionizing radiation is those gamma rays and the X-rays. These essentially are going to cause electrons to be ejected out of the atom, causing this atom now to become an ion. This ionizing radiation can actually be flung out and go straight through a DNA molecule, backbone and everything. If you have a lot of this is eventually going to cause a lot of, it's like tearing a piece of paper up into 100 pieces. When that happens, now we have small pieces of DNA that are just kind of floating there. It can't be replicated. The cell can't go through cell division, and everything shuts down. Non-ionizing radiation is like UV light, and essentially what happens here is the atoms don't form ions, but what they do is they are raised to a higher energy level. When they are raised to this higher energy level, they are going to then cause some formation of bases within the DNA that doesn't allow for adequate or accurate DNA replication. There are abnormal bonds in the DNA. You can do something called cold sterilization, which doesn't mean that we do it in the cold. It essentially means in the absence of heat. And this is using ionizing radiation. Basically, you're going to dose this material with a specific measure of radiation, and it is going to then penetrate and cause the rupture of the DNA, and these are going to then cause these cells to die because it can't go through DNA replication. And remember, if we can't reproduce our DNA, we can't go through cell division. The most penetrating rays in this cold sterilization is the gamma rays, then your X-rays, and finally your cathode ray. There are a number of different applications of ionizing radiation. The first one is the radiation of food products as well as medical products. Non-ionizing radiation is using ultraviolet rays. This again does not sterilize, but it does disinfect. You're going to use very short wavelengths between 100 and 400 nanometers. When you get to this 254 nanometer range, you're going to start to see cells dying. This is not as penetrating as ionizing radiation, but it does destroy a lot of these fungal cells and fungal spores, bacterial cells, the vegetative state, protozoa in either form, and viruses. When we look at what happens with this non-ionizing radiation, I said it made some odd pairing, abnormal base pairing in DNA. If we have a strand of DNA that has adjacent thymines, if it is exposed to UV light, what could potentially happen is that these adjacent thymines will form covalent bonds between the two, and if they're bonded to each other, they can't bond to their adjacent adenine on the other strand. There is a way that the body does go about fixing this. There are some enzymes that are light sensitive enzymes that will go and break these bonds and cause the new hydrogen bonds to form between the adenine and thymines again. But if we get too many of these, you end up with cell death. This is what is implicated in a lot of of a lot of skin cancer is that you have these adjacent thymines and you have several of them in the cellular DNA, and it ends up causing malformation of the cells. Some of the applications that we can use for ultraviolet light, a lot of hospital rooms are disinfected, operating rooms, schools, food preparation areas. If you go to some of these fast food restaurants, you'll see that they use UV light for the disinfection of a lot of their food prep areas. Lots of dental offices. You can also use UV light to purify drinking water. A lot of the bottled water that we get for in our stores right now is UV light treated for purification. This picture over here is essentially UV light water treatment of UV light. Decontamination is a process of filtration of a fluid. This is essentially removing microbes from an air or a liquid. Everything that we've talked about so far has killed the organism. Filtration essentially just separates the organism from a fluid. This fluid is going to be strained through a filter. That filter is going to allow the fluid to pass through, but the microbes are going to stay on the opposite side. So you see you have all of these small pores in here. The liquid or the air or whatever you're filtering is going to go through, and then the microbes are left on the other side. If you look here, you'll see you've got all of these little pores down here, and then all of these microbes that are stuck on the pore side. These are very thin membranes that can be pulled out and actually put on a media source, and you can actually grow up the organisms. When I was in graduate school, one of the things that I did with another graduate student to help him on his project was he took water samples from different places and he ran them through these microfilters, and we pulled the filter off, turned it over contaminated side down, placed it on selective media, and he was able to identify organisms from different water sources and what might be the possible source of contamination. So you can use this filtration method not only to sterilize, but you can also look to see what kinds of organisms you have in a particular fluid. There are a number of different applications for filtration. Any kind of liquid that can't withstand heat can be filtered. The urea broth that you guys use and will use for your unknown, it can't stand heat. Urea will break at high heat, so in order to keep it from breaking, we filter it. Any type of in any type of beverage that you don't want to run through heat to be able to decontaminate, micro brews. People that brew their beer and it goes through microfiltration rather than pasteurization. Again, water for purification. If you go down to the water treatment plant here in Wichita, you will see water going through these enormous filters, and as they go through those filters, the stuff is kept on the outside and the water is purified on the inside. If you have a fish tank, an aquarium, or anything like that, you've got a filter that water goes through, and stuff is left on the outside, and the bacteria then stays on the filter, and the water is purified as it goes through. You can remove airborne contaminants running air through HEPA filters in your vacuum, HEPA filters in your furnace at home. In places in the hospital, you have HEPA filters that will be used particularly in areas where you have a high probability of contamination. Okay, that's our physical methods of control. Let's talk a little bit about some of the chemical agents that we might come in contact with. There are about 10,000 different antimicrobial chemical agents that are manufactured. There are a ton of them out there. Only about 1,000 of them are going to be used routinely in healthcare and in homes. The rest of them are going to be industrial. These can be in a liquid form, a gaseous form, or in a solid form. There are also solutions that are mixed with alcohol or water and alcohol mixtures that are called tinctures. Some of you that are as old as I am can remember something called a tincture of iodine. Iodine is mixed with alcohol to give you this tincture, and it's basically a solution of alcohol and iodine. You need to be able to have some criteria for choosing a microbial chemical. The first one is rapid action, even at low concentrations. How quickly does it work? I want it to work, and I want it to work quickly, and I want to use it as low a concentration as I can. Is this soluble in water or alcohol, and does it have a long-term stability, or does it break down easily? You'll notice that a lot of our cleansers come in opaque bottles, or bottles that you can't see through because they are sensitive to light and will break down easily. Broad spectrum microbial action. Does it target a bunch of things, or does it just target a specific thing? And is it broad spectrum without being toxic to human or animal tissues? Penetration of inanimate surfaces to be able to sustain a cumulative or persistent action. I want to be able to lay it down, and I want it to be able to stay there for a while to penetrate the surface so that I can have a sustained action or a persistent action. Resistance to becoming inactive by organic matter. I don't want my antimicrobial to basically be broken or shut down in the presence of organic matter. Is it non-corrosive or non-staining? We certainly don't want to apply things to a countertop or to a surface that are going to stain that surface or that are going to corrode that surface. Is it a sanitizing, and does it have deodorizing properties? If we have ever had things go bad, food spoil or things like that, you know they stink, and you want to be able to deodorize. You want to be able to get rid of that in the process of sanitation. And is it affordable? I certainly don't want to have to pay $100 for a cleanser. And is it readily available? Do I have to order it? Can I go to the grocery store and get it, or can I go to some particular store and have access to it? You do have some factors that will affect the activity of these chemicals. What is the nature of the organism? Just like with our physical controls, we need to know what is the nature of the organism being treated. What's the nature of the material being treated? What level of decontamination do I need? And what level of contamination do I have? Do I have a little spill, or is it a huge mess? Time of exposure. The longer I leave it on, obviously, the more effective it's going to be. And what is the strength and chemical action of my germicide? Is it, can I dilute it, or do I have to use it at 100%? There are a number of different categories, and I'm going to break these down basically into their chemical groups. The first one are the halogens. These are going to be those chemicals that contain fluorine, bromine, chlorine, and iodine. They are microbicidal as well as sporicidal with longer exposure. So I can put chlorine bleach down, and that chlorine bleach is going to kill spores as long as I can leave that bleach in contact with my material long enough. Basically what they do is they halogenate tyrosine. They attach themselves to the tyrosine molecule and will then break down protein function. Basically, chlorine compounds and iodine compounds are the main chemicals that we use as far as antimicrobials are concerned. We can get chlorine in a liquid as well as a gaseous form. We can also have hypochlorates like bleach, and then chloroamines, which are basically proteins with a chlorine attached to them. These are going to kill bacteria as well as endospores. They are also going to kill fungi and viruses. Probably the most common example of a chlorine compound is household bleach. Iodine compounds, we can use them as free iodine or as I don't know that I can say this word. Iodophores, okay? These are basically topical antiseptics. These are like your betadine. They can also be added as a disinfectant. There is a laboratory iodine called Wescodine that basically is what you use on a countertop. Wescodine, betadine, tinctures of iodine, these are going to be your iodine compounds. I'm sorry, I went back a slide. The next group are the phenols and their derivatives. Phenol is derived from the distillation of coal tar. So this is obviously going to be something that is very strong. You can have high concentrations or you can have low concentrations. Phenols were first used by Lister in his surgical germicide. He wanted, remember, to try and keep people from dying during surgery. They wanted to keep the surgical environment as clean as possible. Basically, there is something called the phenol coefficient, and this is going to compare the chemicals' antimicrobial properties to those of phenol. So if you have a particular chemical and you want to see how effective it is, you're going to compare it to the properties of phenol, and you're going to use this coefficient then to determine the effectiveness. Is it better than phenol? Is it not as good as phenol? In high concentrations, these are cellular poisons. These can actually kill cells. They can lead to cancers, all kinds of things. In lower concentrations, they can inactivate certain enzyme systems, metabolic systems in the cell, and can break down the cell process. The mode of action is essentially they can be membrane disruptors. They can be act as surfactants, bind to those cell membranes and disrupt them, as well as they can eliminate protein function. These enzymes, they are broken and now they don't work. There are some very common examples: triclosan, chlorhexidine. These are all those industrial types of phenols. Triclosan is generally what they put in a lot of soaps, those antimicrobial soaps. And then, of course, Lysol. Everybody knows Lysol. Lysol is very effective. It is a low concentration phenol and works very well. Alcohols are also good antimicrobials. Ethyl alcohol and isopropyl alcohol are the only suitable ones for microbial control. Essentially, what they do is they have a mechanism of action that is going to depend in large part on the concentration of alcohol to water. 50% and higher are going to dissolve membranes. Think about your ethanol in your gram stain. What does it do? It strips that outer layer, and so when you dissolve membranes of these cells, it's going to disrupt that surface tension of that cell, and it's going to cause that cell membrane integrity. It's going to compromise that, and that cell membrane is going to rip apart. If you're at between 50 and 90%, you're also going to have the denaturation of proteins through the coagulation of these proteins. These proteins are going to kind of get gummy and they're going to start sticking together. But at higher concentrations, this doesn't necessarily increase microbial activity. So you're not going to be effective at any higher a concentration. When you get something called absolute alcohol, this is alcohol at 100%, and this is going to dehydrate cells and it's going to inhibit their growth. You're essentially sucking out all of the water in the cytoplasm, and those cells are going to shrivel up and they're going to eventually die. This is a very effective degerminating agent in lower concentrations. Most of our hand sanitizers, the number one ingredient is alcohol. This does not destroy bacterial spores at room temperature, but it can destroy resistant vegetative cells. This is why hand sanitizer is so much better to use than these antimicrobial soaps. It is more effective in inactivating enveloped viruses than non-enveloped viruses, and that is purely because of that lipid envelope. It's going to start destroying that, and it can then get to that capsid much easier. Peroxides, hydrogen peroxide in particular, these are going to be germicidal due to the fact that they are going to have a direct and indirect action of oxygen. Basically, if you've got cells that can't deal with that oxygen, these cells are going to be the ones that are going to be ripped apart. Oxygen forms these hydroxyl free radicals. These are going to be those free OHs. They've got that negative charge, and these are going to be highly toxic, and these are going to interrupt protein function. Proteins, enzymes, they're going to have those hydroxyls bind to those charged amino acids, and they're going to cause those proteins to become non-functional. It also will mechanically remove microbes from cuts and scrapes when you have that bubbling action. That bubbling action actually acts as a scrubber. When it starts to bubble like that, you remove those organisms, and the cell then, or the tissues then, are much cleaner. It is bactericidal, fungicidal, and virucidal, and in higher concentrations, it can destroy endospores. When you get at those higher concentrations, though, those can be very toxic to the skin. So you probably wouldn't use peroxide at those concentrations unless you had some that was probably the only thing that you could use. Surfactants, these are going to be chemicals that have some sort of surface action. These are going to be like soaps and detergents. Soaps, these all are wetting agents. These have a soap is a weak wetting agent. When I talk about a wetting agent, basically what it does is it gets rid of any lipid barrier that's in the way and allows water to get down into the deeper tissues. Detergents are stronger wetting agents. Quats or quaternary ammonias are also surfactants. We'll talk about each of these here a little bit. You have anionic detergents. These basically have very limited microbial power. You're not going to use these very often. But these cationic surfactants, or these cationic detergents, remember, have a positive charge. Cations have positive charges, and they are going to bind well to the negatively charged surface proteins of the bacterial cell. When they bind to those surface proteins, they're going to start ripping those proteins apart, and now we've got these big holes in our membrane, and the membrane then will disintegrate. Soaps are going to be weak microbicides, but they can gain some germicidal value when you mix them with something like chlorhexidine, triclosan, or iodine. These are going to be those antimicrobial soaps. The mode of action of surfactants is that they are cell membrane disruptors. They are going to disrupt that membrane. Those proteins, those stabilizing proteins, are going to be torn away, and you're going to have a huge hole in your membrane. If you look here, this is a great picture, and I think I was talking to Susan a little earlier today about changing the hand washing lab. I know we didn't do the hand washing lab in your class, but basically, if we look at a non-germicidal soap versus a germicidal soap, you'll see that a non-germicidal soap, we will have this fluctuating line where eventually we will start to trail off. But in a germicidal soap, the action of that germicide gets into the deeper tissues and continues to get down into the cells and will kill them, clear down into the resident flora that we would be getting to after a certain number of time. You do have some heavy metal compounds. These are going to be things like mercury, silver, gold, copper, arsenic, zinc. These are going to have some significance as germicides, particularly mercury and silver. These have what they call an oligodynamic action. Basically, they are going to have an effect in an exceedingly small amount. We don't have to use very much of it to cause an antimicrobial effect. Oligo means small, okay? Some examples of these heavy metals that have this dynamic effect are merthiolate, mercurochrome, silver nitrate. Merthiolate, mercurochrome, these are old medicines. These have been around for years and years. This is the stuff that makes your skin red when you put it on. Silver nitrate, this is what they put on the eyes of babies when they're first born to prevent against neonatal conjunctivitis. If a mother has gonorrhea, when she delivers, the baby could potentially have gonococcal conjunctivitis. They put silver nitrate in the eyes to prevent that. The mode of action is that it binds to the functional groups of proteins like the amino group and the carboxyl group, and it inactivates them, and it keeps them from being able to bind to each other to make these long proteins. So you're going to start breaking down these proteins, and they're going to become non-functional. You do have some drawbacks using metals in microbial control. They can be very toxic to humans. Lots of these heavy metals, if you get too many of them, can have a very toxic effect, and they can actually be carcinogenic. Oftentimes, they can cause allergic reactions. Lots of people are allergic to silver. Lots of people are allergic to copper, and so these don't always work. Large quantities of fluids and wastes are going to neutralize these actions. So if you're somebody who is on a heavy metal regimen, drinking lots of water can actually minimize the effect. You do have some microbes that have developed resistance to these heavy metals. So again, there are some drawbacks. One of the heavy metals that has been kind of making some headlines now is zinc. All of these antiviral medications that are over the counter that you can take. I can't remember what they're called right now, but when you begin to feel the symptoms of a cold or some viral infection, you start popping those, and that zinc gets in there and binds to the capsid of the virus and essentially destroys it. Here's a great picture. You've got basically a silver amalgam and a piece of gold foil, and you can see around the surface of that you're going to have a lot of a relatively large zone of inhibition. I know that doorknobs and stuff like that are not heavy metals, but metals of many kinds have a significant microbial effect. And so bathroom doors and things like that are not quite as bad as people make them sound. Aldehydes are another type of germicide. These are going to, remember, you have your two aldehydes. You have your medial one, which is essentially your ketone, and then your terminal aldehyde on that terminal carbon. Glutaraldehyde, formaldehyde, formalin basically is the aqueous solution of formaldehyde. Are the ones that are most often used, and essentially what they do is they are going to disrupt enzyme and protein function. They're going to insert themselves into particularly the peptidoglycan of the cell wall, or they're going to insert themselves into the outer membrane of the gram-negative cell wall, and they're going to basically disrupt the function of those proteins and those enzymes within the cell. You have some gaseous sterilants like ethylene oxide. These are going to either sterilize or they are going to disinfect. Basically, these are going to target nucleic acids and proteins. These are what we call alkylating agents. They are going to insert themselves in specific positions in proteins and in nucleic acids and essentially cut them off. They're gonna stop their function completely. Nucleic acids, the messenger RNA doesn't work, the DNA doesn't work. In your proteins, if they're enzymes, they get shut down. Other proteins, they change their shape, and everything turns off. You have three particular gaseous sterilants: your ethylene oxide, your propylene oxide, and chlorine dioxide. These are all three very common sterilants and disinfectants. The ethylene oxide is what is used to sterilize the plates that we use in the lab. You do have some dyes, just like the dyes we use in lab, that can be used as antimicrobial agents. Actually, these were what were used in the day, and they are the primary source of certain drugs that are used in chemotherapy. Aniline dyes like crystal violet, malachite green, these have a specific effect against gram-positive bacteria and a number of different fungi. Yellow acridine dyes, these are certainly not any that we've used in the lab, but they can be used in wound treatment. These are safe to use on the skin. You do have some limited applications because they do stain. You certainly wouldn't want to walk around with this big purple smear on a cut or something like that. But they do have some good properties. They are narrow spectrum, however. They are targeted for a specific organism, like a gram-positive or a gram-negative or a fungus, and they do stain, and so that can be problematic. Acids and alkalis. Very low or very high pH can destroy or inhibit microbial cells. They will interfere with the function of enzymes. They will interfere with the function of proteins. They do have some limited applications because they are very corrosive. They can be very caustic to tissues and hazardous in nature. Acids burn, alkalis burn, and so on tissues they can be very they're not going to be used very widely. But on surfaces, if say you need to etch something, a lot of times you will have acid etching. They will go in and put that acid on a surface, spray it off with water, and it will be etched in. It will have eaten away on that surface. So you could see if it's going to eat away at a hard surface, what it might do to tissues. Here is a table that I think is a very nice table. I can't remember if this was taken out of your book or if it still is in your book. I got this from the last edition. But it tells you the product name, what its chemical agent is, and is it what is its antimicrobial category. Is it a detergent? Is it a halogen? Is it an alcohol? What does it do? And so you can see kind of the products that you're using. A lot of us use Clorox disinfecting wipes. We use Ajax. We use Dawn dishwashing liquid. We use Pine Sol. All of those kinds of things. Scope mouthwash. You could actually get drunk on that if you drank enough of it. You'd have to drink an awful lot of it, but you could. Its specific chemical agent is ethanol. Ethanol is what you drink in alcoholic beverages. So you could also drink Purell hand sanitizer. I don't think it tastes as good as Scope, but hey, give it a shot. Anyway, this gives you kind of an idea of some of the things that are very common that we use for microbial control.